Hi, and welcome to the next section here in our chapter on regularization. So here we'll take a brief look and also at other forms of penalties. So we'll discuss that L1 and L2 regularization actually induce bias. Well, I guess that's what we mean when we say they shrink parameters. So we could also say that this is the price we pay for them being a countermeasure against overfitting, but maybe there are other alternatives which introduce less bias. So we'll take a look at LQ quasi norms for regularization. We'll take a look at L0 regularization, which I guess is something we would like to do for feature selection, but which is computationally somewhere close to infeasible. And then we'll take a look at more modern forms of penalties like the SCAD and the MCP. So yeah, I guess we already understood this. Ridge and Lasso, they have very many nice properties, but they are biased estimators. In a certain sense, that's how we constructed them. And this bias doesn't necessarily vanish even if sample size goes to infinity. I guess that's also a very relevant point. So we could think that this bias goes away when we have larger and larger sample sizes in front of us. That's not true. So even for the case for orthonormal features, one can directly compute the bias. So here this expected value between the estimated parameter and the true parameter. And this is not necessarily zero. Yeah? So it's zero if the true parameter value is zero, but for these two other cases here, it's not zero, and you can see the concrete expression in front of you. So there are a bunch of other estimators which we could now use if we become, I don't know, unhappy about this bias which exists here even in the limit of infinite sample size. So I'll not go too much into details here, but I'll introduce and summarize things briefly. So if we're using L1 and L2 norms, I guess we could in general just look at any form of LQ norm, LQ quasi norm. What can we see from this? So here again, I've visualized the two common cases for L1 and L2, but here you have also, for example, Q equals 4 or Q equals 0.1 and some other cases in between. So you can immediately see is that for Q less than 1, the penalty becomes non-convex, which the penalty itself, the penalty structure I guess we like, but the non-convexity I guess we don't like too much because it makes optimization way harder. On the other hand, does what we want, it will introduce less of this bias. For Q larger than 1, no sparsity is achieved, and usually these things, we do like them also to do feature selection, and we like this sparsity inducing property, and usually we don't like losing that. So yeah, these non-convex LQ norms for Q less than 1, they actually have some nice properties, like an oracle property. So they allow consistent and asymptotically unbiased parameter estimation, and they allow variable selection. That's pretty nice. On the other hand, like I already said, optimization is harder, so it's non-convex, so there isn't a guaranteed unique global minimum, but there can be multiple local minima. I'm not going to show too much on these, but I'll show more on MCP and SCAD, which kind of behave in similar ways. Before we do this, let's discuss L0 a little bit. So at the limit of these LQ norms, we make Q smaller and smaller and smaller. So you can see here how the penalty structure looks like as a function of the theta parameter value here. And at the end, if Q becomes 0, then you get this non-continuous thing where the norm is 0 if and only if theta is exactly 0, and it's 1 if theta is the absolute value of theta is larger than 0. So basically what this does is it just counts the number of non-zero parameters. And I guess if you're interested in feature selection and having a sparse model in terms of the number of included features, that is potentially exactly what you want. So this will induce sparsity a bit more aggressively than L1 does, but it really doesn't shrink parameters, which you might also like because it doesn't introduce this bias, which we just discussed. You can see things like ARC and BRC, which you might know from linear model selection, as special cases of this L0 norm. I won't discuss this here more. Also, it's obvious that L0 regularized risk is now neither continuous nor convex. I mean, this makes it really hard to optimize, and actually you can show that this becomes NP hard to optimize. So it's, yeah, for larger n and p values, for medium values, this might be tractable. Very often you also then can rewrite the problem basically as a discrete optimization problem, and we have become way better at solving these things efficiently, but for large n and p values it can still be close to intractable, or optimization at least can become extremely slow. And how to do this more efficiently, I would say, is still a matter of current research, which I really won't discuss here at all. Now, for SCAD and MCP. So what is this acronym? What is SCAD? SCAD is short for smoothly clipped absolute deviations, and the name basically describes the Frankenstein structure of our penalty here, because the penalty is actually made up of 3 different parts. So we have let's take a look here at this plot. I think it's easier. You can read the formulas, they are not super complicated, but let me explain them here through the visualization. So you can see the LSU here, so that's the L1, so that's just the absolute value of theta. It's easy to understand, we've seen the plot before, and currently we are discussing SCAD, so SCAD is the red guy here, okay? So how is that? So I'm really bad at drawing things, but I'll try. So this is actually made up of 3 parts. So you have this inner part here, which is basically the absolute value, well, times some scaling constant, and then there is a second part which is quadratic. Here you can begin seeing me being really bad at drawing, and then so that's like part 1. That's part 2, and then there's a constant part, which is part 3. So this is 1, this is 1, this is the linear part 2, the quadratic part, and then the constant part 3. And because this becomes here constant, this is what ensures that the thing doesn't become too biased, in the end. It's also a smooth function. You can see this from the plot. So you can handle this in optimization. It's at least continuous and differentiable. That because of the non-convexity, that's the price you pay for not having this bias estimation. It does become harder in optimization. And this is similar thing, the MCP, this is for minimax concave penalty. Again, it's a definition on intervals. So you have a first part here, which is basically quadratic, and then again a constant part here at the end. So MCP is the green curve. You can see here the comparison to the other two, so to the LSU and to the SCAD. So MCP starts by applying some penalization rate in a similar manner as LSU. It's not exactly linear, but it's close to this, and then smoothly reduces this rate to 0 when theta becomes larger. So in comparison to SCAD, this MCP thing, it immediately starts relaxing the penalization rate, and SCAD, this rate remains flat until we reach a certain size of theta here, larger than lambda. It's really nice that both SCAD and MCP, they possess this oracle property. They can consistently select the true model as n goes to infinity, while LSU might actually fail here and doesn't necessarily do that. Here's a short example, simple example, comparing SCAD, MCP, and the LSU. So we'll again compare coefficient paths. So I'll use a very simple DGP again. So again, it is something linear. As you can see here, you can see the true coefficients here. You can see that some of them are 0. Actually, it's a super high dimensional space now. And only the first 4 features actually have a true effect, which is non-zero. And we sample 100 samples from this very high dimensional space. And we now look at the coefficient paths of LSU and SCAD. And what you can see is that I've also marked the optimal positions of lambda. So I guess we could ask what's now the kind of optimal model under cross-validation. So what's the optimal penalization we should use? I've computed that from 10-fold cross-validation and marked it here as vertical lines. And you can see for these optimally selected models from cross-validation, the LSU actually undermates the true coefficients? Well, a little bit. Yeah, well, SCAD and MCP achieve an unbiased estimation, and also because of this better variable selection, you can also see that here for these are all of the coefficient paths for the noise variables, and they are estimated more to exactly 0 for SCAD and MCP than for the LSU, okay? Yeah, especially at the optimal selected lambda. And what I would have liked to show a little bit more is that you can see here the bias. So they would be unbiased if we would be exactly here at this flat position where these guys are exactly 4, well, not 4, 4 and minus 4, and these two guys here are 2. Well, actually, to be honest, I'm a little bit wrong about this, because you can, actually maybe the example is a little bit better than I said. So you can see here the lines, right, of 4, minus 4, and 2, and minus 2, and you can actually see here this bias, right, especially maybe for these two guys. So especially also at this optimal lambda position, you can see that x 3 and 4, they are not exactly 2 and minus 2, they're a little bit less, and this is exactly this bias that we talked about. While for SCAD and MCP, you don't really observe that. Yeah, you get nearly exact, unbiased 4 and 2 values, well, in absolute value for this example here, which, like I said, is quite simple, but I wanted to finish at least with something concrete so you can see the effect of these techniques. Okay, that wraps up things here. See you in the next session.